project on the integration of AESOP into NGL tools. Don't worry too much about the acronyms, they'll be described later on in the presentation. My name is Bob.
I'm Henry.
Bryan. Samson. And so as we begin, we'll go into an overview about our presentation so you can kind of track along. We're going to be starting off with the background, kind of what field of study we went into and why we wanted to go into it, as well as the current methods for approaching this field of study. And then we'll follow that up with how we decided to study that field. And then we'll have a little demo of how our final kind of outcome came. And we'll go into how we want to change that up in the future, or improve it, and then a little bit of a question at the end. So for background, what we're really focusing on is proteins. And we're all bioengineers here. We understand proteins are very critical to many of life's functions. Without proteins, basically you wouldn't be able to survive. So a good way to understand the properties of proteins and predict how they're going to work is to look at their electrostatic potentials. Right? Basically what that is an idea of how positive and negative each part of the area around that protein is, and it works as a good indicator of how well it'll bind to its ligand and so forth. So if you look at that red and blue map, that's kind of a visualization of the electrostatic potential of the protein. It's also known as the AESOP contour map, in which each part of that bubble is of the same level of charge, except that I believe it's red. Yeah, red's negative and blue is positive. And by using this, finding an electronic way to kind of predict what the electrostatic potentials are going to be allows for us to save a lot of time as well as resources, because trying to do this in a wet lab environment and finding out experimentally can become very costly and as well as take a lot of time. So finding a different way to approach this will actually help you plan out your experiments better, and that way you can save money and time.
So Bob mentioned a lot about electrostatic potentials and things of that nature, but in order to get those values, you have to calculate them. And what we do is we use the linear Samson equation. We use this equation because it allows for multiple dielectric coefficients, unlike Gauss's law. So if you see here, what's actually done computationally is you embed a protein within a grid, within a three-dimensional grid, and depending on the size of the protein, you will choose the appropriate size grid. So that grid will be broken up into smaller cubes, and each cube will be solved with the linear Samson equation to obtain the electrostatic potential at that particular focus space. And what you have to do is you have to specify many things like dielectric coefficients of both protein and solvent. And then you also have to define the ion accessibility function, the ionic strength, things of that nature. As you can see up here, you can see everything that goes on within the electrostatic potential grid that needs to be calculated.
Currently, we have several different methods that several different programs that help us aid us in analyzing proteins between groups. We have AESOP, which is an adaptive protein protein solver. This is software that uses Boltzmann equation and evaluates the electrostatic properties of molecules and proteins. We have BMD and PMD, which are both molecular theories that we use to view a protein. But AESOP, the analysis of electrostatic similarities of proteins, software actually developed here at UCR. What the software does is, as the title suggests, we can use this to compare the similarities and differences in electrostatic potentials of our proteins. The problem with this current method is you have to have all these programs installed. You have to call each and every one of them up individually to perform one single task. What our goal was to take the features of all these programs, combine it all into one package, one program. That's going to make things a lot easier for us, make things a lot faster, and that's what we're trying to do by incorporating AESOP into NGL tools.
So the main thing that we had to do in our project was implement AESOP in the programming language Python. It was originally developed in R, developed by Chris Kieslich. And so what we first had to do is actually you take a protein of interest and you have to do mutations on it. So what you see here is you run through the protein, select a particular amino acids of interest, mainly charged amino acids, such as glutamine and lysine, and then from there you have to isolate each amino acid. Each protein, And once each one of these proteins are isolated and changed that discharged amino acid to an alanine, you perform the electrostatic calculations for each, and then you see what one of them. So that way you can tell the differences between the electrostatics. The way we tell the difference between and the electrostatic potentials is calculating the ASDs. So basically what you do is you iterate through the grid that I mentioned before, and you look at the differences between each point space. So up here, you take the difference between point A and point B of the two proteins, and you divide it by the max of the protein, and you sum up all the differences. And that will give you this grid right here. That will tell you this is how similar this protein is to this protein, to this mutant. And go through all that. And once that's done, you have to cluster them to see how similar or dissimilar all the different mutants are to each other.
Yeah, so when a protein gets very large, looking at a chart like this can be expanded much larger, and it become very difficult to kind of determine how close and similar they are by having to look at the numbers, right? Because once again, you're just dealing with more numbers then. So what we did is we clustered the protein family, the members of the protein family together, such that those with closer numbers were grouped together, and then those with larger numbers were grouped away. With the lower the number means the more similar that they are to the parent complex. And so it ends up looking kind of like a family tree where brothers are closer to one another and cousins are further apart. Right? So ultimately, we would end up with a dendrogram that looks kind of like this, which very quickly and visually you can see, okay, here's the parent branch, and here are the most closely associated ones. And then you can decide to move on from there, which protein you want to choose for your experiments and to kind of verify and what that environment.
So most of you guys have probably taken the computer science class, and you guys know how difficult it is to debug and things of that nature. So obviously we ran into problems as well. Again, since it was a new language for all of us, we ran into many different little problems, just like syntactical errors and things of that nature. But we had a lot of different, really big technical problems. One of the main ones was a memory usage error. What we tried to do originally is save all of the electrostatic potentials from all the proteins into one large array. But this was a huge problem because each electrostatic potential in that file has over 2 million data points. So if you have a protein that's somewhat large, like we ran it on C3D and that has 64 ionizing residues, that was over 128 million data points. So that's a very large array, and Python couldn't handle it. So we didn't know about that until we ran it on such a large protein. And that was one of the bigger problems that we ran into. So this was fixed by only opening 2 files at a time, being 2 files that were being compared. So that was a major issue that we ran into, and it was resolved fairly easily. Another problem we had was operating systems. As you all know, you see a lot of Macs, a lot of PCs, very few Linux machines. So the biggest problem we had is just trying to get the program to run on all 3 systems. The biggest one we had is Mac. We couldn't get APBS to run a lot of it. So we had to abandon the Mac operating system and try to get it to work on the other 2. So ultimately we had to start narrowing them down until we had to work on Windows.
Right, so here's a quick demo program. If you notice the timestamp at the beginning, it's 9:27. It kind of gives you an idea for even the small protein, how long it takes. So it starts off by opening the host program, Python molecular viewer. And so as it opens, you'll notice that you can load up any protein file, a PDB or PQR file, and it gives you kind of basic functions of any molecular viewer. You can view it, turn it around, you can do a lot of calculations to it. But as the initial compute menu will show, it doesn't have an AESOP button, right? So we have to load it up ourselves. And it'll allow you to do a lot of things. But for our program, basically follow what's shown here, but load our command system into it. And that way it doesn't have to waste time loading in case you don't want to use it at that time. But as it does it, if you look in the compute menu, you can see that AESOP is now there. And so click on it, and run, and then ask for some simple parameters. Can you tell me the name of the protein? What do you want for your biological coefficients? Do you want to use the standard default ones we have? So you tell it yes or no. And then it begins to run these electrostatic potential calculations by automatically calling APBS when the program is that integrated in. And this also takes some time. We let it run for a couple of times so you can kind of get a feel of how long you have to wait if you're either programming this or actually using it. So most people probably run this and then leave, do something else and come back. This is for the first mutant now. It's taking some time. And what it's doing is it's solving that Poisson-Boltzmann equation. So if you notice, Henry kind of paused recording and come back in as electrostatic calculations finished. And now it's kind of sorting it through and then drawing the dendrogram, which will come as follows. The resolution on ours is pretty bad, and we'll have to tamper with the settings so that it'll be able to come out. What it comes out is the different mutant names and the groupings and the clustering similarities. Right now, most of them are in pairs or singles. You can change that depending on the thresholds you give it. That's still something that we're experimenting with, but ultimately, this is what we end up. If you look at the timestamp, it's now 9:44. So for a small protein that had 10 residues, that took a total of 17 minutes, which isn't too bad.
For future work, we want to make the program more user-friendly. We want to get it user-friendly, but we want to make it even more. We want to make it a browser for the user, so you get the files from the file system. We also make a sequential contour pentagrams, and they're supposed to look like this. The first number represents the location of the protein, and the other number represents the mutated amino acid. And we also want to make free energy applications. These are our acknowledgements. We want to thank welcome in the back. We also want to thank Chris.
Kiss it! Woo! Sorry.
We also want to thank Shahai and Rosa.
Questions?
We have about 3 minutes for questions.
Shelby, it was not clear in which platform at the very end your framework works.
Ultimately, we got it to work on Windows machines. Yeah.
So it was the problem with the Mac, was it APBS or PNB?
No, it was APBS. We mainly had problems with PNB and a lot of Windows 7 machines, but luckily Bob had a Windows XP network that we got it to work on.
On your diagram, are there labels to say, to help point out which protein is
Yeah, the little blurry things at the end.
Oh, those are the names.
Those are the names.
So it tells you the host parent name.